This is Lhasa, the spiritual home of Tibetan Buddhism. This city in the clouds is one of the highest, most inaccessible on Earth. Situated on the vast Tibetan Plateau, it is surrounded by not one, but three mighty mountain ranges.
Before the 1950s, there weren't even any roads to get to Lhasa, just meandering mountain paths that took months to get through and only in good weather. But the Chinese government came up with an audacious scheme to connect this ancient province with modern China.
This is the highest railway on the planet. Specially designed high-altitude locomotives climb to over 5,000 meters above sea level to cross the Tibetan Plateau, the highest and largest mountain plateau on Earth.
Our locomotives can pull 3,700 tons of cargo, or 20 passenger carriages. It's the most advanced technology in our country.
The engineering is extraordinary. 675 bridges and 10 tunnels to cross the frozen wilderness that's known as the roof of the world.
Whenever I see the train passing through the Tibetan Plateau, I feel extremely proud.
From Beijing and Shanghai in the east, trains run to the city of Golmud, the start of the high-altitude line. From here they begin their climb, crossing the formerly impenetrable Kunlun Mountains to reach the immense frozen Tibetan Plateau. At this altitude, the air oxygen content is half that at sea level, and temperatures can descend to -30. The railway reaches the world's highest station at the Tanggula Pass, a staggering 5,068 meters above sea level, before making its way to Lhasa.
This is the Qinghai-Tibet line, a railway which at first people thought was impossible. It's called the Heaven Road, and honestly, that's what it is.
It's the most audacious railway project ever imagined, and comes with some enormous challenges.
How do you build on terrain that's frozen solid in winter and boggy marshland in the summer? How can a train be powered at altitude that's normally the preserve of aeroplanes? And how do you communicate with trains when they're in the middle of this vast wilderness? But perhaps the biggest challenge is how do you keep everyone breathing?
At this incredible altitude, oxygen is in short supply. Dr. Zhu Xinxian is in charge of the railway's medical unit.
On the Qinghai-Tibet Railway between Golmud and Lhasa, the average altitude is over 4,000 meters. It's an area of extremely low atmospheric pressure. There's only around 50% oxygen in the air here compared with the mainland.
The human body is not designed to cope with such low oxygen levels. It can lead to potentially fatal altitude sickness.
The most common symptoms of altitude sickness are headaches, vomiting and confusion. It's vital that correct oxygen levels are maintained and any deficit is dealt with immediately. In severe cases where the body's starved of oxygen, it can cause swelling of the brain or lungs, which can be fatal.
These unique trains are specially engineered to protect their passengers as they travel through this beautiful but brutal landscape. Ding Weiyan is the senior engineer.
In here is the oxygen generator, which pumps oxygen into the train carriages. These prevent oxygen shortages at high altitude and make passengers feel more comfortable. Inside, there is an altitude sensor to determine the oxygen levels outside and oxygen concentration sensors to monitor the levels in each passenger compartment. The train is made up of 16 carriages. And each of these carriages has its own oxygen generator, like this.
The passengers also have access to oxygen masks, which they can use if they're having difficulties.
Well, if you're just sitting here, then it's all right. But if I climb to the top bunk bed, then I notice that I have some shortness of breath.
As an extra precaution, the railway posts a medical team on every train.
There's a doctor and a nurse on board all the passenger trains. They carry oxygen and heart monitors, oxygen cylinders, and a full medical kit. Once they're on the train, they do a patrol every 3 hours to check on passengers.
These extra measures on board ensure safe passage for the 2 million travellers who make the journey every year. But the team who built the line didn't have these luxuries.
Construction workers are at a high risk of altitude sickness and hypoxia, a severe lack of oxygen. Doing physical work means your body uses up oxygen very quickly. That made this an extremely difficult project. At first, we thought there was no way it could be completed.
They would need to turn to a machine from the past to defy nature and build across the roof of the world. Humans have never let a lack of air stop them from going to the most extreme environments. Mountaineer George Mallory lugged a 14-kilogram oxygen tank up Mount Everest. Ancient Greeks used diving bells to explore the depths. But the oxygen didn't last long, and the bell could tip over. And when railway pioneer Isambard Kingdom Brunel wanted to bridge a deep, fast-flowing estuary, he sunk giant metal caissons and pumped in compressed air to create a pressurised environment to build the foundations. But while the engineering was sound, it wasn't so great for the workers. Dr. Gary Smurden is in southwest England at the site of Brunel's masterpiece, discovering how experts in engineering and medicine came together to solve the problem.
So here we have the Royal Albert Bridge, a fantastic feat of engineering. Most of the people who travel across the top of this bridge do not have the faintest idea about the effort and the suffering that went into building this bridge, because the feat of engineering to get that pier built down into the rock bed of the river was very new at the time, very dangerous, and they didn't really understand what they were doing. These workers were moving into a pressurised environment every day to do their digging and their engineering, and then coming back to the surface. There were 25 workers. 1 died, 2 became paraplegic, and all of the others became ill due to what became known as caisson disease.
With 19th century engineers wanting to build ever more impressive structures, a way to treat workers who came down with caisson's disease had to be found. In 1876, American inventor Daniel Kelly submitted a patent in Chicago for a compressed air bath, a machine that would hold the key to treating workers with caisson's disease. The body contains nitrogen gas. When the pressure increases, this gas dissolves into the blood and tissue. But when the body returns to normal pressure, it becomes a gas again. If bubbles of nitrogen gas form, they can gather in joints and tissues, causing serious problems. Kelly's machine was a forerunner of the hyperbaric chamber.
Any problems, just put your hand up, say stop, and we'll take it from there.
Lovely, see you on the surface.
Whilst the condition affecting the caisson labourers was very different from what the Chinese workers were suffering from, this amazing machine holds the key to solving both problems. An air compressor creates pressurised air which is stored in a giant tank. It's slowly pumped into the airtight hyperbaric chamber, recreating whatever pressure environment doctors need to treat their patients. This was the key to treating caisson's disease, giving doctors the ability to reduce those deadly bubbles in the blood.
So here you are, we're in the chamber now. The door is shut. My colleague Chris is at the controls, and he'll soon be pressurising me and getting me down to the equivalent of 30 metres.
And the machine itself can actually be used to demonstrate the very problem it was built to solve with a simple experiment.
So with me here in the chamber, we have an empty bottle here that's full of air and another bottle that's full of carbonated water. We'll see what happens to them on the way down.
Stand by, blowing down the Comex.
The empty bottle contains air at normal sea level air pressure. So as the pressure in the chamber mounts, the bottle collapses.
Okay, let's shoot at 30 metres, Gary.
Okay. I'm sat here at 30 metres. One of the biggest changes is my voice. That extra density of the gas causes it to pass differently of my vocal cords, and I speak in a very strange manner.
The water, which was carbonated at normal air pressure, has completely lost its fizz.
And there we have a glass of carbonated water. At this pressure, the gas molecules are dissolved in the liquid, but the gas is still in there.
This water represents blood in the body.
So when we go back to the surface, you will see bubbles will start to appear. Now that's exactly what was happening to these caisson workers. When bubbles will start to appear in your blood and in your tissues, as a human, you're in trouble.
It was discovered that the key to avoid bubbles forming was a slow ascent, giving the body time to equalise. This machine allowed doctors to simulate a slower controlled ascent, saving the lives of caisson workers.
Oh, because here we are, back on surface again. It's nice to be out. Now we know how to come back up safely. As you saw, it's a slow ascent. In the old days, take the top off the valve and reduce the pressure, and people bubbled inside them, and that's what caused all the problems. But now I've been down, I've come back up to surface, absolutely no problems at all. Feel the same as I did when I went down.
In China, the team building the railway realised that this 150-year-old chamber could be put to a different use.
On the 29th of June 2001, the build began of the highest section of the railway. This was the base hospital for the construction team. We provided a lot of medical personnel and support. This hyperbaric chamber was used frequently.
The construction team went through 120,000 bottles of oxygen each year, but even that wasn't enough.
There were many critically ill patients during the construction of the railway. Our medical staff were first on the scene to give initial treatment and, if necessary, to transfer the patient to the hyperbaric chamber. These chambers were vital. They saved patients' lives.
When you're working at 4,000 metres altitude, getting back down to sea level isn't easy. But by placing workers suffering from altitude sickness into hyperbaric chambers, they could effectively simulate a move straight back down to sea level, meaning treatment could start immediately.
Engineers installed 25 chambers at strategic locations along the 1,100-kilometre line.
During the construction of the railway, the success rate for saving lives from acute altitude sickness was 100%. There were no fatalities. This line is a milestone in the history of railways. I'm proud of it, and I'm very proud of being part of the medical team during its construction.
This machine helped keep the 100,000 workers who spent 5 years building this inspirational railway safe. With construction crews hard at work to link Lhasa to the rest of China, the biggest engineering challenge still lay ahead.
If the ground melts below your foundations, you're in real trouble. A railway line is at risk of collapse, derailing any trains trying to use it.
Mount Everest, the highest mountain in the world. The Himalayas make up the southern edge of the world's largest mountain plateau. Stretching 1,000 kilometers north, the Tibetan Plateau is the breathtaking setting for the highest railway on Earth.
In the past, people thought a railway to Lhasa could never be done. It's one of the most remote cities in the world. But this didn't stop the Chinese engineers, and the engineering challenges they faced were immense.
The city of Golmud sits at 2,800 meters in the foothills of the Kunlun Mountains. To link it to Lhasa, engineers needed to find a way to run rails across the permafrost, the permanently frozen ground of the 2.5 million square kilometer plateau beyond. Wang Xingchang is Professor of Engineering at the Railways Research Institute that was tasked with achieving the impossible. He regularly makes the 8-hour round trip from Golmud to the heart of the plateau to monitor the ground conditions.
The area we're in now is typical of the Tibetan Plateau. It's called no man's land. 2 or 3 meters beneath us is permafrost, which is permanently frozen ground. It's incredibly cold here. The annual average temperature is between -2 and -7 degrees. It's these low temperatures that create the permafrost on the Tibetan Plateau.
Building anything in this environment isn't easy.
Frozen ground can actually provide the perfect foundation for building on, but with one important condition: it must remain frozen. If the ground melts below your foundations, you're in real trouble. A railway line is at risk of collapse, derailing any trains trying to use it.
So how do you keep hundreds of kilometers of ground frozen solid enough to build on? For inspiration, the engineers turn to another frozen territory 7,000 kilometers away. Known as the last frontier, Alaska is America's northernmost state. Straddling the Arctic Circle, it covers a staggering 1.7 million square kilometers. When the largest oil field in North America was discovered in Prudhoe Bay, a 1,300-kilometer pipeline down to the southern port of Valdez was required to export the oil. The problem, just like in Tibet, was that they needed to build on endless expanses of permafrost. Local civil engineer Doug Goering is aware just how hard this can be.
So this is the type of vegetation that's typical of permafrost terrain in interior Alaska. If you take a stick and you push it down into the moss layer, you find that all of a sudden you hit something hard and it just won't go any further. What I've hit is the top of the frozen layer of ground. And so that frozen layer is roughly this far below the surface of the moss. Trying to build any kind of engineering structure on this type of permafrost results in major challenges. If you try to build a warm structure like a house or a building, you can imagine that the heat from that building is going to work its way into the ground. It thaws the ice in that ground out and it becomes a mushy mess. The house foundation typically fails.
And when you're trying to build a pipeline that will carry warm oil, those problems are compounded.
Normally, an oil pipeline would be buried, but anywhere where the ground is frozen, the pipe has to be physically separated from that frozen soil because, of course, it carries warm oil. That warm oil would melt the frozen ground and cause structural problems, cause the pipe to deform, buckle, and probably would have caused oil leaks.
So they built it above ground. This is the Trans-Alaska Pipeline, an $8 billion creation that carries up to 2 million barrels of oil a day across the entire state.
As you can see, it's a very large pipe, roughly 1.3 meters, 48 inches in diameter. It's full of oil. It's been full of oil since the late 1970s. The design focused on an elevated pipeline to keep the warm pipe away from that frozen ground.
But the foundations for the support columns still needed to rest on solid, frozen ground. If it melted, whole sections of pipeline could collapse. Luckily, one man had an answer. In 1963, nuclear physicist George Grover developed a system to transfer heat that would be crucial for engineers trying to build on permafrost.
You can see that each of these vertical support members are capped by 2 finned sections. Those fins sit on top of a device known as a thermosiphon. These thermosiphons are used to ensure that the ground that the vertical support members go into remains frozen. the vertical support members rely on that frozen ground strength to hold the pipe up.
A thermosiphon is essentially an empty tube which goes through the marshy bog down to the frozen ground. At its base is a liquid refrigerant with a low boiling point. When the temperature rises in the ground, the liquid absorbs the heat, starts to boil, and then evaporates, dissipating the unwanted heat through the tube and into the atmosphere, keeping the ground around the foundations cool.
What I have here is a canister of butane, which is similar to the refrigerant that's used in the thermosiphon. And what I'm going to do here for our demonstration is get a little bit of liquid butane into this plastic bag. So you can see that I have liquid in the bag here. What happens at the base of the thermosiphon is that liquid boils. And you can see that when I add heat by putting my fingers on this bag, that I get pretty vigorous boiling of the butane. This is the same thing that's happening at the base of the thermosiphon. In this case, the butane is collecting heat from my fingers. In the case of the thermosiphons, the refrigerant collects heat from the permafrost and pulls heat out of it, dumps that heat into the atmosphere.
Over 100,000 thermosiphons help to keep the oil flowing.
This pipeline project really is an engineering marvel. It's been stable for on the order of 40 years. Really, I think it's safe to say that the engineers who designed this solved the permafrost challenge.
The permafrost challenge has not beaten the team in Tibet either. Here they've used the thermosiphons on a massive scale, stretching as far as the eye can see to cross over 500 kilometers of permafrost.
These thermosiphons are the best way to solve the problem. It's a great solution. Its main function is to decrease the temperature of the ground and prevent the permafrost from melting. This is the part that releases heat. And this is the middle section, and the working part is underground. We use 2 rows of thermosiphons on the side facing the sun and 1 row on the side which doesn't face the sun.
Over 25,000 thermosiphons have been installed. But with the heat generated from passing trains, the thermosiphons alone aren't enough to keep the ground frozen and the foundations solid. The track is also raised off the ground on a crushed rock embankment. This low-tech engineering works by letting the cold wind flow through the gaps between the rocks, dissipating any heat coming from the trains above.
By using these measures, we protect the railway by keeping the ground cooled up to 15 meters away from the track. This prevents the permafrost from melting and sinking the railway.
But for an 11.7 kilometre stretch of the permafrost zone, in the heart of the plateau, neither of these measures could help.
We're now at the Chamawa River Upland Plain Natural Reserve. This is all wetlands. The biggest feature here is the hydrothermal lakes. This is a natural occurrence of frozen soil.
Whilst in the winter this area is frozen solid, the heat from the hydrothermal lakes means it's all a boggy marshland come summer. So this is the incredible solution. At over 11 kilometres, it's the longest bridge over permafrost in the world.
Most of the frozen soil is melted here. A rock embankment wouldn't be stable, so we built a bridge. The bridge is supported by pile foundations which are inserted deeply into the ground. In this environment, a bridge is a much better solution than an embankment. The biggest difficulty for us building this kind of bridge is working in winter. During summer, the atmospheric temperature is too high. If we built during this season, we would risk causing the permafrost to melt, making it too unstable.
Working through winter at temperatures down to minus 30 degrees, engineers achieved the impossible and completed the final, most difficult part of the line to Lhasa.
Building a railway in the permafrost of the Tibetan Plateau was one of the biggest engineering challenges in the world.
With the groundbreaking line complete, engineers still had another major hurdle before any trains could use it.
Regular locomotives just wouldn't be able to cope with the lack of oxygen. They wouldn't get anywhere near Lhasa.
The Tibetan Plateau is known as the roof of the world. Crossing it is the highest railway on the planet.
The engineering that's gone into this project is mind-blowing. It was almost impossible to conceive of a railway running at this altitude. It's an extraordinary feat of human ingenuity.
To construct this £3 billion line, engineers overcame huge hurdles. But coming up with a locomotive that could handle the altitude almost scuppered their ambitions. Across most of the China railway network, electric locomotives are used, which draw their power from overhead cables. The Shanghai to Lhasa Express uses these for the first part of the 47-hour, 4,300-kilometre journey across the country. But when the train reaches Golmud, it runs into trouble.
In the isolated high-altitude plateau, extremely low winter temperatures combined with lightning storms means that electricity supply cannot be guaranteed. So they can't install the overhead cables necessary for electric trains.
Normally, railway engineers would turn to a regular diesel locomotive.
Combustion engines need fuel and oxygen to work, but at these altitudes, there's just not enough oxygen to give enough power to the engines to haul the huge trains up the steep gradients required.
Internal combustion engines draw air into the combustion chamber to mix with fuel. The piston compresses it, then the spark plug ignites it. This controlled explosion forces the piston back down the cylinder. But as oxygen levels drop, so does the force of the explosion and the power produced.
Regular locomotives just wouldn't be able to cope with the lack of oxygen. They wouldn't get anywhere near Lhasa.
To get trains to run at such high altitudes, the engineers needed to look to the skies. Mechanical engineer Dan Dickrell is exploring Pikes Peak, one of the highest points in America's Rocky Mountains. It was here in 1918 that a landmark experiment changed engine design forever.
Driving this really muscly car up one of America's most iconic highways is quite exciting from both an engineer and an auto enthusiast perspective. The terrain is twisty. It's a wild ride for sure.
But as the road climbs, the amount of oxygen in the air falls.
I've reached the halfway point of Pikes Peak. For my body, I can sense the lack of oxygen through my lungs. My lungs are telling me there's not enough oxygen in this air. I cannot perform at peak efficiency. I can feel that lack of oxygen at this altitude, and so can the automobile. The bottom was really snappy. It's starting to get a little bit more sluggish.
At the 4,302-metre summit, the oxygen is almost 50% lower than at sea level.
All right. I can really feel it. Lightheaded, do not feel great. Now on the way up, the internal combustion engine inside my car, it could feel it too.
This problem plagued early aircraft pioneers, who found the higher they took their machines, the more their engine's power faded. And during World War I, the ability to fly high became a matter of life and death. The higher a plane could get, the smaller the chance of it being detected by the enemy. Just like the engineers in China, they had to find a way for their engines to cope with lower oxygen levels, so they could go higher than ever before. To help the US Army Air Force solve their lofty problem, they drafted in steam turbine engineer Sanford Moss.
Sanford Moss developed a revolutionary piece of machinery that would force more air into the airplane engine, essentially turbocharging it.
Moss's turbocharger was a total game changer. Instead of just being wasted, the engine's exhaust gas is used to spin a turbine, which in turn powers a compressor which draws in air, compresses it, cools it, and pushes it into the combustion chamber. This high-pressure mix, when ignited, dramatically increases the engine's power. To demonstrate the difference it makes, first we need to see how an engine performs without it.
This is going to serve as my cylinder. Inside the cylinder, we're going to put a mixture of fuel and air. Instead of gasoline, I'm going to use butane. Now what I'm going to do is I'm going to take this butane and inject it into my cylinder. And 2 metal electrodes are going to serve as a spark plug. I'm going to introduce 2 alligator clips that will provide electricity in 3, 2, 1. Cool. All right, now we're going to repeat the same demonstration, except this time I'm going to turbocharge the cylinder. To do that, still need some fuel. Now this time we're going to introduce a slightly different cork because this one has a valve in it. That's going to allow me to pressurize the cylinder just like a turbocharger would. We lock down, give it a few good pumps. So now I've got my pressurized cylinder. Let's repeat and see what the effect has on it. In 3, 2, 1, go! Whoa, nice! Oh, that one flew much, much higher. The turbocharged cylinder worked much better in terms of explosive release of energy, just like a turbocharged engine would.
In 1918, Moss and his team came here to carry out their first high-altitude tests. He put his new turbocharged engine on the back of a truck and attached it to a giant propeller. The output had been 230 horsepower, but with his new invention, it was boosted to 356 horsepower.
Three years afterwards, a biplane fitted with a Moss device broke the altitude record, flying higher than any other airplane had flown before. Turbochargers exist all over the place. Really impressive pieces of technology.
In China, engineers have fitted Moss's turbocharger to special locomotives to give them the power to cross the high-altitude Tibetan Plateau. At Golmud Station, locomotive engineer Shen Deji is monitoring the switchover.
This train has just arrived from Beijing to the east. It's an electric locomotive, powered from the overhead cables. After the crew have disconnected all the wires, it will be pulled out so that the new locomotive can come in.
With the passengers eager to continue the next 14-hour leg of their journey to Lhasa, the train crew must move quickly.
This is our solution to the high-altitude problem. It's a tailor-made plateau diesel locomotive, especially designed for the Qinghai-Tibet line. It's about to be connected to these carriages.
These turbo diesel engines provide 6,000 horsepower to pull either 20 passenger carriages or a whopping 3,700 tons of freight at speeds of up to 120 kilometers an hour.
I had the honour of driving the first train to cross the plateau to Lhasa. So whenever I see this incredible advanced locomotive coming into Golmud, I feel excited, very excited. If we'd not managed to build this turbocharged locomotive, so many people just wouldn't be able to get to Lhasa. I feel very proud of this solution.
But the engineers still face another major hurdle. The single-line design makes reliable communications essential.
With high-speed trains travelling in opposite directions in some of the most remote locations on Earth, how do you ensure you can communicate with them to keep them safe?
The highest railway in the world runs to Lhasa station. Trains on this line are specially engineered to cross the frozen tundra of the Tibetan Plateau. Undercarriages are sealed to protect against frost damage. And even the windows are specially designed to cope with sub-zero temperatures.
The windows are equipped with a special heating device. It prevents the glass from freezing and cracking as the train travels along the cold parts of the Golmud to Lhasa line.
These incredible advances make this previously impossible journey possible for passengers like Gregor and Marianne, tourists from Holland.
Yeah, it's definitely amazing. I'm reading a book right now about a woman who's traveling in Tibet, I think about 20 years ago. And it was so different. You had to do everything by foot or with a jeep. And if there were mud floods, then you couldn't go any further. It's really a totally different setting to just cruise through the mountains in a warm train.
The 1,142 kilometers of high-altitude railway between Golmud and Lhasa includes a staggering 675 bridges and 9.5 kilometers of tunnels, including the highest railway tunnel in the world, the 1,338-meter-long Fengguoshen Tunnel, drilled through a permanently frozen mountain.
Building this line really pushed the boundaries of engineering. But with a £3 billion price tag, they simply couldn't afford to build two lines side by side, one for each direction. So they had to settle for a single line. This presented engineers with a new challenge. With high-speed trains travelling in opposite directions in some of the most remote locations on Earth, how do you ensure you can communicate with them to keep them safe?
So, how could an innovation from 19th century railway pioneers help inspire the engineers in China? The early 1800s was boom time for Britain's railways. Thousands of miles of new tracks were laid. But with more trains, they needed a way to communicate. Early systems relied on flags being waved by hand.
Come on!
Or from horses galloping alongside. But with more trains travelling further and faster than ever before, these systems were totally insufficient. Something had to be done. Engineer Kate Mulcahy is at Miniature Wunderland in the German city of Hamburg, the largest model railway in the world. 1,300 trains with over 10,000 carriages crisscross this huge attraction, where they have a similar problem: keeping trains safe.
Luckily, an ingenious new form of technology was about to change the way the world communicated, setting in motion a telecommunications revolution.
In 1837, William Fothergill Cooke and Charles Wheatstone struck upon a brilliant concept.
Here I have a compass, an electric wire, and a lantern battery. The breakthrough that Cooke and Wheatstone discovered was that by using these simple ingredients, you could send messages over really long distances. It works like this. If I attach one end of my electric wire to the positive terminal on the battery and then attach the other to the negative, I create a complete circuit. This induces a magnetic field which should deflect the needle on my compass to the right. If I reverse the terminals, so I remove this one, now attach it to the negative, this one now to the positive, what you'll see is the needle now deflects to the left. By using the simple method of electromagnetic deflection, Cook and Wheatstone had discovered the first ever form of electronic communication.
The first test took place between two London stations, Euston and Camden Town. A telegraph wire was laid in a tube alongside the track with a special device at each end.
Cook and Wheatstone built this instrument, the 5-needle telegraph arranged on a grid of letters. Now in my version, my construction here, this bit represents the sending element, and then this bit over here represents the receiving element. These rods in the middle represent wires. Now because this telegraph, the sending one, is connected in the circuit to this telegraph, when I move this needle one way, the action is mirrored in the receiving telegraph over here. So for example, if I wanted to spell out, say, the word stop, I start with the letter S. So on my sending, I'll move this needle so it points towards S, and I'll move this needle so it points towards S. And then the person on the receiving end will look for where the points of those needles converge. I then need to move the needles so that I can get them to converge on T.
This device enabled its users to spell out words and send them down the wire.
Their feat of engineering brilliance was to send the first communication electronically on the railways.
The needle telegraph started a telecommunications revolution. Adopted by the railway network initially, it soon went round the world.
Eventually, Cook and Wheatstone streamlined this system into just one needle that through a series of movements could create a coded message. This system of signalling lasted on the railways well into the late 1930s.
In China, they've taken this 180-year-old concept and given it a 21st century makeover. Third-generation railwayman Wang Jianmin is deputy manager of the Golmud depot.
Between Golmud and Lhasa, we use satellite positioning signals. You won't see a single trackside signal on the Golmud-Lhasa line. We use the satellite positioning signals due to the tough weather conditions and 4,000-metre high altitude. This is a great piece of technology. It's a massive leap forward.
The train control system is run from a control room at Xining Station, with global positioning satellites determining the train locations. All signalling is virtual. Instead of wayside signals used by Cook and Wheatstone's system, all information is communicated directly into the train cab, where an onboard computer terminal displays up to the second information to the driver.
The advanced technologies implemented along this line are unique in this country. They are the only reason that we can provide Tibet with the Heaven Road Railway that's been so important for their economic growth and social development.
The Golmud to Lhasa line has transformed travel across the Tibetan Plateau.
Business increased quickly once the Golmud to Lhasa line opened. Just in the last year, we've dispatched over 1 million passengers. And the goods we have transported by rail have sharply reduced the number of lorries on the road. Lifestyle products, building materials and daily necessities such as oil are basically all transported by rail now.
Building a railway line across the roof of the world was never going to be easy.
When we were young, we didn't think there would ever be a railway between Golmud and Lhasa. I think it's a milestone in the history of global railway.
The unprecedented and ambitious project stands as testament to the tenacious perseverance of the human spirit.
If this special locomotive didn't exist, so many passengers wouldn't be able to get to Lhasa. So I feel very proud of this train.
Go! Whoa, nice!
By building on the work of the inspirational pioneers of the past, upscaling and breaking new ground themselves, the engineers have succeeded in making the impossible possible.
The Qinghai-Tibet Railway is the greatest engineering achievement in the world.